All right, this is the part I know you've all been waiting for. You want to talk about how exponentials can be used in daily life, right? So there are so many different applications we could look at. A very common one to study in a math class like this is actually related to money growth. So I'll go ahead and pick on that one just because money is something that we all have to understand a little bit, but just know that we could apply it to population models or other things that you may find more interesting. So I'm going to write down two formulas. You perhaps have seen these, so we'll dissect them and then we'll demonstrate using them. But if you are investing money, there are kind of two formulas at a simple level that we could understand to predict the growth of your money. So the first one will look like A equals P times 1 plus r over n to the power of nt. And this one is going to talk about how money grows with respect to how often it's compounded throughout the year. Another common money growth formula that, again, you may have seen before is going to be A equals P e to the RT. And this one is specifically reserved for continuous compounding. So let's dissect a little bit what these different letters are standing for, and then we'll do some examples. So in both of these models, A, P, R, and T mean the same thing. That's why I just wanted to write them both down right away so that we could chat about both at the same time. So A is going to be basically the account value, how much money you have after a certain amount of time passes. P, we typically refer to P as the principal. Or for me, it's a little easier to think about it as the amount of money I'm investing. So if you walk into the bank today and say, I've got this much money I'm going to invest, that would be the value of P. R, as we see in both formulas, R is the rate. So of course we hear that talked about sometimes as the APR, and it's expressed always as a decimal for these formulas. So R is the rate as a decimal. Let's talk about T next because T does occur in both formulas, and then I'll leave N for last because it's only in the first formula. What do you think T stands for? T is time, and for these models, again, you can use other models for money growth, but in these two situations, we're using time measured in years. So time in years. I know a lot of times, like if you get a car loan or something like that, right, they talk about months, but for these two money growth models, we'll use time in years. Okay, so then N, let's mention N. It occurs twice in the first formula because in the first formula, the number of compoundings per year will vary. So N is the number of compoundings within a year. I don't have to include N at all in the second formula because it's understood to be compounding continuously. So the reason I don't have any N's here is this is compounding continuously. Okay. So in terms of different values that are common for n, there are going to be some keywords to watch out for. So if it says it's compounded annually, that's going to mean n is 1, right? There's one compounding per year. If it says it's compounded semi-annually, we'll understand that to mean twice a year, so n would be 2. A couple other common words, quarterly could come up, so 4 quarters in a year. So if it's compounded quarterly, the n value is 4, and then maybe another one we could encounter would be monthly. So in that case, it would be compounded 12 times within a 1 year span. Daily n would be 365, those kind of things. So just with this knowledge, let's go ahead and look at using the formula in a very straightforward way. And throughout the unit, we'll be able to solve more complicated problems with this model. So I hope you're taking notes always, but for sure, make sure you're jotting down these formulas. So make sure you're jotting down A equals P times 1 plus R over N to the NT, and A equals P times E to the RT. Cool. All right. So I think just in terms of looking at the formulas, that should feel okay. When we get to an example of continuous, I'll talk a little bit more about this e here because e is actually a number, kind of like pi. So we'll talk about it when we get there. All right, first example. Let's say that we were asked to talk about how much money there's going to be in an account a couple years down the road. So how about we know $5,000 is invested. So if $5,000 is invested into an account, and I want to make this kind of fun, so I mean, maybe assume it's Monopoly money or something, but let's say we were able to get a really good rate. I'm going to say 9%, which is like crazy. So 9% interest. And let's say we're able to get compounding monthly. So the more compoundings, the better. How much money, right? How much money will there be in the account after, and let's try to be a little patient because the longer we wait, as you can guess, the more money there will be. So let's give it 15 years. All right, so a lot of information. That's kind of typical of a word problem, right? So as with any type of application, I like to take my time and make sure I understand super clearly what I know, what I'm finding. So I like to start by just writing down the formula again. And especially if this formula is newer to you, gives you a chance to get familiar with it, even if you're not, memorizing it, at least you get more and more familiar with it. And then on the side, what I'm going to do is just jot down the A, P, R, and T values, A, P, N, R, and T values. I'm going to try to keep that same color coding going. A, let's see, P I had in green, R, T, and I left N for the last. So in this formula, there are 5 different values, and I just want to figure out which of these 5 do I know. Algebraically, I think you would agree with me. If we have 4 of the 5, we should be able to solve. And at this point in time, a specific 4 out of the 5. So as we read through, $5,000 is invested. So is $5,000 a value for A, P, R, N, or T? So 5,000 is how much you put into the account to begin with. So this is going to be the principal, that amount of the initial investment. So P will be $5,000. It's invested into an account earning 9% interest compounded monthly. So 9% is another value for our formula. Hopefully that feels to you like a rate of the investment. So this is going to be the rate. Now 9% as a decimal would be 0.09. So anytime you have a percentage, to write it as a decimal, you just need to kick the decimal 2 places to the left. So we'll get 0.9 or 0.09 as the rate of the investment, which is amazing. And then it tells us that we're compounding monthly. So there's that keyword to tell me a little bit about the N value for my formula. So monthly tells me it's compounded 12 times per year since there are 12 months in a year. And let's see, the other thing we're told is we're going to sit on it for 15 years. So 15 years is definitely a value for time. So it looks like in our problem here, the unknown value, what we're solving for, will be the A value. And that's again, how much money will be in the account after all this occurs. So in terms of the math involved, this is actually a very straightforward calculation because you can see what we're solving for is A, which is already isolated. So it's just really a matter of plugging and chugging. So I'm going to start plugging in what we know. I'm going to put in the 5,000 for the value of P, the initial investment. Then it's always 1 plus because basically this is saying you're going to earn, you aren't going to lose what you already have. So there's your 100%. And then this is the extra percent on top of that from interest. So I'm going to plug in the 0.09 for our rate. I'm going to divide that by 12. And then that's raised. This is why this is an exponential application. It's raised to the power of n times t. Okay. If you're comfortable on your calculator and you know how to use parentheses appropriately, you are more than welcome to punch that whole thing in and get your correct answer. What I'm going to do is a little bit more step by step, just because often at the beginning this can be a little tricky to know how to approach this. So if you want to do more of a step by step, go ahead and do 0.09 divided by 12, which should give us 0.0075, and add 1 to it. So I'm just having us clean up the parentheses a little bit more. So 0.09 divided by 12 is 0.0075, and then we added 1 to that to get 1.0075. And then for the exponent, just do 12 times 15. That should give us 180. So I'm cleaning up a little bit before entering in the calculator. You may have, if you know how to use parentheses carefully, typed it all in at once. Cool. So this is a good time to get to know your calculator. Some of you have what we call forwards calculators, so you can like literally type it as you see it. Some of you may have more of a backwards calculator. I'm going to kind of share with you what the final output should be so that you can play around on your own calculator until you get this value. And actually, you can use Desmos too, so I'll go do this on Desmos and pop right back over. Cool, so I just jumped out over to Desmos and punched in what I had written on the screen here. And I'm going to write my answer now on our screen, making sure I understand that my answer is money. So rounding to the nearest cent is normal. In some problems it may say nearest dollar, because if you're dealing with thousands of dollars, I guess a couple cents maybe isn't that big of a deal. But let's be precise and round to the nearest cent here. So when I typed in 5,000 times 1.0075 to the power of 180, I'm getting back $19,190, and I'm going to round to 22 cents, right? The 6 after the 1 tells me to round it up to 22 cents. So this means if you invested that initial amount of $5,000 and you're able to find this amazing interest rate of 9% compounded monthly, in 15 years, you will end up with this amount in the account. So make sure you're able to get that on whatever calculator you're using, whether it be Desmos. Desmos, obviously, I would say is probably the most simple, and hopefully you guys have been using it. If you happen to have a standalone calculator, try it out on that. If you're on your phone, you have to be a little bit more careful, but that works too. So let me know if you have any trouble getting that value, but hopefully that's looking pretty good. Let's just do one last example with the other formula, and then we'll call it good for this video. So let's consider if we had $7,000 this time, and it's invested into an account with continuous compounding. So as we mentioned a little earlier, continuous compounding tells me I'm using that other formula. Continuous compounding. Sometimes spelling and talking doesn't work too well for me. So, and let's say the rate of the investment was the same as the last problem. Let's do that 9% again. Super cool, 9% APR. And let's sit on this for 10 years this time. So same punchline, how much will be in the account? And we'll approach this very similarly to our first example. Just because of that word continuous, I'm going to be real careful to note that my formula I'm using is the A equals PE to the RT formula. Anytime we have continuous compounding, we're going to use the formula that involves E. And we'll just jot down A, P, what else do we need? We need R and T. So continuous tells me that we're using the E formula. $7,000, what value is that to you guys? A, P, R, or T? Hopefully we feel that's the amount we initially invested, so that's the principal. That goes in for P. We're getting more comfortable with rate as a decimal. I use the same rate as before, so 9% would be 0.09 as a decimal. We don't have to worry about n in this problem because it's compounded continuously, so it never stops compounding. We are given the time value of 10 years. So with that understanding, it seems clear then that we're solving for A, which is how much money are we going to have after, it sits there continuously compounding at 9% for 10 years. So plugging in, we have 7,000 for P. E is a number, as I mentioned before. It's similar to pi. It's about equal to 2.71. I say it's similar to pi because it's another one of those irrational numbers. Never repeats, never ends. And then we plug in our rate and our time. So this one is actually even easier to punch in the calculator. The only thing I would maybe recommend doing is just timesing your exponents together. So the 0.09 times 10 would be 0.9. And then you are ready to punch this guy in. So Desmos works well, standalone calculator. Just make sure you can find the E button. On a lot of calculators, you're going to have to find a little button that says LN, which is something we'll study as we go on in this unit. And you may have to hit a second key to access the E through the LN button. So I'm more than happy to make a separate video on calculators if anybody has questions. So just let me know and I will happily add that video in too. But assuming you're okay punching this in on Desmos, you can just use the letter E and it will know. But I'm getting back about $17,217.22 rounded to the nearest cent. So that's how much money would be in this account after 10 years if it compounds continuously at a 9% interest rate. So pretty cool application, right? Hopefully that makes some sense. I look forward to hearing from you all what you think.